movement alert triggers at 2 a.m., relying on an engineer to wake up, log in, diagnose the issue, and apply a fix guarantees the attacker wins. Modern multi-cloud threat vectors spread across clusters in seconds, meaning human response speed is mathematically insufficient to stop an active breach. This diagram shows the legacy approach to remediation. It operates on a straightforward three-step loop. The system generates an alert, a human reviews it to create a remediation script, and finally, they push a patch deployment to the vulnerable server. But watch what happens to this linear loop in a 2026 environment running on ephemeral workloads. When hundreds of temporary server nodes rapidly spin up and disappear every minute, the sheer volume of transient data overwhelms the rigid three-step process. The system literally fractures under the scale. Because legacy patching moves too slowly to catch temporary assets, enterprise applications are left entirely exposed to lateral movement. To close that gap, defense mechanisms have to move away from linear scripts and shift toward context-aware automation. Let's trace how this automation works against a specific complex threat, an exposed API secret sitting inside a public-facing virtual machine. This network graph shows how modern cloud-native application protection platforms, or CNAPs, map those relationships. Instead of treating the VM in isolation, the platform's security graph traces a direct path from the public-facing VM through that exposed secret and straight into a highly sensitive internal database. The system calculates this specific chain of assets as a toxic combination. It filters out the isolated, low-severity vulnerabilities surrounding it and prioritizes this exact path because it gives an attacker a clear route to critical data. This automated, context-aware filtering directly addresses severe developer alert fatigue. By automatically hiding thousands of low-level warnings that don't lead anywhere, security teams are only prompted to look at actual, exploitable attack factors. Without a graph calculating how these assets interact, engineers are effectively paralyzed by notification noise. This automated prioritization provides the essential filter that makes real-world cloud defense possible. Once the threat is prioritized, we enter the response phase. This split-screen diagram shows the transition from generating simple scripts to enforcing autonomous cloud policies. Instead of spitting out a generic Python script, the platform's automated playbook dynamically builds a step-by-step policy configuration file tailored to this exact environment. The immediate concern for any engineering team is that automated remediation will accidentally break the live application. To prevent a production outage, the platform routes the newly generated policy into a simulated CI/CD pipeline. It passes it through validation checkpoints, like a Terraform plan check, to prove the fix is safe before it ever touches production. Now, pause the video for a moment and think through this problem. If the security platform successfully pushes a patch to a running container, what happens when your autoscaler spins up a brand new container 5 minutes later? The new container will boot up using the original flawed configuration. To achieve a permanent fix in an ephemeral environment, the remediation cannot target the active runtime. It has to rewrite the underlying infrastructure as code template. If your auto-remediation workflow causes system crashes, or if it only patches temporary instances that get overwritten minutes later, it provides zero value. Deep, reliable integration with existing DevOps pipelines is what actually separates 2026 platforms from legacy scanners. With validation passed, the platform autonomously pushes the updated configuration to the source code repository. The repository then pushes a secure update to the database environment. Fixing the root template completely severs the attack path, neutralizing the threat at the source. This cheat sheet infographic outlines the 4 essential pillars required for a modern remediation workflow. First, detect and graph the environment. Second, prioritize the toxic combinations. Third, simulate and validate the fix in a CI/CD pipeline. And fourth, execute autonomous enforcement at the code level. Mastering these 4 pillars gives organizations the ability to stop lateral attacks in real time without sacrificing application uptime. Whether you are evaluating Wiz, Orca, or any future CNAP, this workflow establishes the baseline requirement for securing a modern enterprise stack.